Hello everyone, welcome back to the another session in Design and Analysis of Algorithms. The topic name is Hamiltonian cycles with backtracking, and this topic you'll find in third unit as topic number 10. Let's get started. Hamiltonian cycles. Let graph is equal to v comma e be a connected graph. This is what the prerequisite to generate Hamiltonian cycles with n vertices. Graph should be a connected graph with n vertices, and the definition of Hamiltonian cycle is Hamiltonian cycle is a round trip path. That means if you started visiting of vertex from A, after you complete the visiting of all the vertices, again should go back to the starting position. That is what round trip. Now, round trip path along with n edges of graph G that visits, every vertex is once and returns to its starting position. Now, the next is, in other words, if a Hamiltonian cycle begins at some vertex V1. Now, let's see that 1, 2, 3. Now, V1 belongs to G. Now, let us assume that it is V1. Now, it is belongs to graph G. And the vertices of G are visited in the order V1 comma V2, that is visited order. I have visited V1, that is 1. Then as I found the path in between 1 to 2, the next visiting vertex is 2. That's what V1 comma V2 up to Vn plus 1. Then the edges Vi comma Vi plus 1 are in E. So this is what connected graph. Now, so let's see about few examples which graphs will generate Hamiltonian cycle, which we will not. Now, let's understand what generate from connected graphs as we were discussed in the previous. So, do I have any Hamiltonian cycle from this graph? Let's find it out. How many Hamiltonian cycles you will get from this graph? So, what any Hamiltonian cycle from this graph? Let's find it out. How many Hamiltonian cycles you will get from this graph? So, what we learned from the previous slide, that visiting of all the vertices for one time, and where you were started to there only you have to end. Now, keeping in mind the definition of Hamiltonian cycle, now let's write the possible Hamiltonian cycles what you can get out of this graph. Now, 1 comma 2, that is 1, 2, 2, and the second 2 I have, there is a path. Now, 1, 2, 6, 5, 4, 3, 1. It is also one of the possible path to generate Hamiltonian cycle. And is there any other way? 1, 2, 6. 1, 2, 6, 2, 2, 5, 4, 3, 1. This is also one. So, there are many Hamiltonian cycles from this graph. Now, we'll see the other also. From 2 I am starting. 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 1, 1 to 2. So, if I write this one, you can see the first one what we were considered as the first path. Now, in this 2, only starting vertex is different, but the visiting path is the same, 3, 4, 5, 6. So, you cannot treat this as a different Hamiltonian cycle. You cannot include into the different number. It is the same. Though you change the starting vertex, it is same. The path is same. The visiting order of the vertices are same. Hence, it is as same as your first path. So finally, this graph will help you out to generate Hamiltonian cycles. And why it is generating Hamiltonian cycles? Because it is a connected graph. Now, let's see the next example. Now, let's see this one. Do I have any Hamiltonian cycles? Now, let's see. 1 to 2, 2 to 3, 3 to 5, 5 to 4, 4 to 1. Yes. So, 1 to 2, 3, 5, 4, 1. Still, do you have any other chance? 1 to 2, 2 to 4, 4 to 5, and 5 to 3, 3 to 1. This is also one of the Hamiltonian cycle. So, this is also connected graph. That's what you could able to see the Hamiltonian cycle, at least one, and at most you have Hamiltonian cycle which are n. Right? Now let's see this one. Do you have any Hamiltonian cycle? Can you generate any Hamiltonian cycle from this graph? Let's see. 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. If I wanted to go back to this one, I cannot go back from 8 to 1. I have to again visit this vertex. So this path is not correct. Now, let's see. Is there any other path which is possible from this graph? Let's see that also. Now, that the path is what? 1 to 7. Let's see this whether it is correct or not. Otherwise, we'll take this one. 1 to 2 and 2 to 8 and 8 to 7 and 7 to 6, 6 to 5, 5 to 4, 4 to 3 and 3 to 1. Now this is a possible path. That is the path 1, 2, 8, 7, 6, 5, 4, 3, 1. So this also can generate a Hamiltonian cycle. So all these three graphs are what? Connected graph. Connected graph. That's what you could able to see Hamiltonian cycle. Now let's see. This is one of the graph. And this graph is what? Can you generate any Hamiltonian cycle from this graph? Let's see. Let's check. As you did not find any edge from 4 to 5, 4 to 7. And 4 is in the middle point, right? If you wanted to visit 1 to 4 to 6, then how you can go back? As you did not find any other edge from the 6, you cannot have any Hamiltonian cycle, right? So let's have a trial. 1 to 5, 5 to 6, 6 to 7, 7 to 3 and 3 to 4. So you did not have this path, this path, this path. Hence you cannot have any Hamiltonian cycle from this graph. Now let's see this also. And this is what? 1 to 2, 2 to 3, 3 to 4. And again you have to go back to 2. So Hamiltonian cycle is not possible. Because see, this 2 is what? It is an articulation point. So what is an articulation point? I'll show you even this graph. This graph also you can say this is articulation point. Now, first of all, know what articulation point is. Then you can know why Hamiltonian cycle is not possible from that. Now, articulation point is what? A vertex V in a connected graph G is an articulation point if and only if the deletion of the vertex V together with all edges incident to V disconnects the graph. So if I delete this vertex, then I cannot find the edge from 5 to 1 or 6 to 4 or any of the vertex from this side. So articulation point is what? It is a junction to connect to two different vertices. So if I delete this vertex, I am calling this as articulation point, because articulation point is what? A vertex V in a connected graph G is an articulation point if and only if the deletion of vertex V together with all edges incident to V disconnects the graph. So this is articulation point. If I delete this one, this 5 comma 6 will not have any edge to this side. So 3 is a what? Junction. If it is a junction, if I wanted to visit 5 vertex, I have to go via 3 and again come back to via 3. So you cannot visit one vertex for 2 times. It's only for single time. Hence Hamiltonian cycle is not possible from articulation points. And now let's see this one. We'll take an example. And there is one more important thing what I have to talk. So in the previous question paper, this is the question what it is. Biconnected graph. What is biconnected graph? And give an example for a biconnected graph which generates Hamiltonian cycle. Now let's see what is biconnected graph. A graph G is a biconnected if and only if it contains no articulation point. Did you find any articulation point? If I delete this vertex, If I delete this vertex, still this vertex is in connection with 1. If I delete this vertex, still it is having a connection with 4. So, deleting of any vertex in this graph will not affect the other vertices. So, this is not articulation point. If you see this one, no articulation point. Now, if you see this graph, this is articulation point. Articulation point, if I delete this one, this will be a separate one, as you did not find any edge in between this 5 or this 6 to any other node. So, now biconnected graph is what? A graph G is a biconnected graph. A graph G is a biconnected if and only if it contains no articulation point. Now it is a biconnected graph. Now, we'll see the example how backtracking is applicable on Hamiltonian cycle. So the backtracking solution for this problem is defined as x1 to xn, where this x1 to xn or belongs to number of vertices, or in other sense you can tell it is n is equal to number of vertices. In the graph I am going to have x1 to xn. Now the backtracking solution vector x1 to xn is defined so that xi represents the ith visited vertex of the proposed cycle. Now we all need to is determine how to compute the set of possible vertices for xk. If x1 to x of k minus 1 have already been chosen. Now the vertex xn can only be the remaining vertex, and it must be connected to both xn minus 1 and x1. We begin this function which is next value of k, which determines a possible next vertex for the proposal cycle. Now let's understand the algorithm of this Hamiltonian cycle. I am just taking x1 to, this algorithm uses the recursive function of backtracking to find all the Hamiltonian cycles of a graph. The graph is stored as an adjacency matrix G 1 to n, comma 1 to n. All cycles begins at node 1. Now, so we will be going to take next vertex function to generate the values for x of k. Now, this next value is what assigns a legal next value to x of k. Initially, we are beginning with x of k double equal to 0. Now, it is return the same vertex. If k value is equal to n, then we will print all the vertices what we were visited. Print in the sense that we will write all the vertices which are visited. If not, we will again increase the index of k. That means visiting the vertex from 1, and we will start the same algorithm till it find the complete path of visiting. Right? Now, let's see this example. We'll trace this example, how Hamiltonian cycle will works. So, we are at k vertex. Initially, your k value is 0. We are working with this vertex. Now, so what is Hamiltonian cycle? Hamiltonian cycle is to find a round trip path. That means it has to know whether edge is there, the next vertex from this vertex to other vertex. So first of all, before you going to find the Hamiltonian cycle, you need to know what is the next vertex. For this, there is a next vertex function, and here I am writing some array which is x1 to k minus 1 is a path of k minus 1 distinct vertices. If x of k double equal to 0, then no vertex has been assigned to x of k. X of k is equal to 0 in the sense initially no vertex is assigned. After execution, x of k is assigned to the next highest numbered, and that is the very reason we were taking this for loop. For loop is what? Initially it is 0. When it is 0, we will return the solution that the graph is this one. If it is not, we will start with j equal to 1. Now, x of j double equal to x of k, then it is break. If j double equal to k, then we will check whether the vertex k less than equal to n or it is equal to n. If it is if both the conditions are true, in this any one condition has to be true, then we will be going to evaluate the next vertex. So this is what finding the next vertex in the graph. Right now, so how backtracking is useful over here? What we will do with the backtracking is, it's very simple to understand. We'll take some backtracking approach. Now, according to the backtracking, whatever vertices you have, you just make one note, that is 1, 2, 3. Now, what I'm going to do is, after I visit the first vertex, I can go to second vertex or third vertex. Based upon what we will move, we will be taking cost adjacency matrix. No, the cost adjacency matrix will tell you whether the connection is there from other node to this node or not. Now we'll take here itself, as I have some graph. We'll take here 1, 2, 3. So I have completed visiting the first vertex. So if I wanted to move to the second vertex, you should know whether the path is existed or not. Let's check 1 to 2. Yes, path is there. And once after I check this one also, I'll move to which one? Third vertex. Again, you should know whether the path is there or not. 2 to 3, do you have any path? 2 to 3, do you have any path? Yes, you have. So it is also valid. And again, check 3 to 4. 3 to 4, do you have any path? 3 to 4, yes, you have. So when you have 3 to 4 also, it is a valid path. Now when it is not valid, now let's see. If you can find the edge to 1 to 3 or 1 to 4, among these 2, 3, 4, which is valid, that you have to check. 1 to 2, I have an edge. 1 to 3, do I have any edge? Yes, it is also valid. 1 to 4, I don't have any edge. So you have to kill the node. Exploring of the nodes will be stopped from this fourth vertex. So we will not. So again we will come to this 2 vertex, and again you have to think in such a way which vertex is having connection to which vertices. Based upon this adjacency matrix only, we'll perform Hamiltonian cycle. So as far as bounding function is concerned into this algorithm, so bounding function, if you don't find any edge in between 2 vertices, that it will ignore it, that it will cut from the tree. So this is about Hamiltonian cycle of a graph. And this is your lab experiment also. You try to implement a code based upon this algorithm using Java programming. Thank you all.